I think we can get started actually. I mean, people are still coming in, but it's yeah. Okay, so today it's my great pleasure to welcome Michael Köhl here. Michael Köhl did his undergrad actually in 3 different places, in Heidelberg, at MIT, and in Frankfurt. He then went on to do his PhD in Munich with Ted Hensch, and after that spent some time in Zurich at ETH as a postdoc in a group of Tilman Esslinger, and then went on to Cambridge for a period of 6 years. And since 2013, he is a professor at the University of Bonn. And during his career, he received numerous awards, for example, the Wolfson Research Award of the Royal Society or the Thomson Medal and Prize. And he basically has done a lot of research on all things that are cold: bosons, fermions, boson-Fermi mixtures, 1D, 2D, 3D. And I'm very excited to hear more about something in between today, namely a bilayer 2D system. So.
Okay, let me share the screen. So first of all, thank you very much for the very kind introduction and also for the invitation to speak at the seminar. It's great that we can do it by Zoom and at least keep up some communication during this difficult times. Yes, so I would like to talk today about our recent work with ultracold atoms in optical lattices, particular ultracold Fermi gases. And I will discuss with you the realization of 2-dimensional systems, as well as the realization of bilayer Hubbard models, and what kind of phases we can see in those. So the basic motivation for this research is that we would like to study strongly correlated quantum matter. So that is quantum matter where we have an interplay between kinetic energies and interaction energies, and also dimensionality in our specific case. And the hope or the aspiration is that we can use this interplay to generate new collective effects. And of course, this has a very long and rich tradition in condensed matter physics. And one of the prime examples of a strongly correlated phase in condensed matter physics is, of course, high-TC superconductivity, the origin of which we still don't understand very well. And in these condensed matter systems, the big challenge is that to really get a microscopic understanding for the physics that is at play, because often we don't have enough control, or we don't have good enough observation capabilities to really see and understand what is going on at the microscopic level. And over the past 2 decades, essentially, ultracold atomic gases have kind of filled a gap in this quest, because they allow us, on the one hand, to realize phases of strongly correlated matter. The first example was the Mott insulator transition in the bosonic atoms, for example, and then also the BEC-BCS crossover studies, which started by 15 years ago, and more recently the studies of fermionic matter in optical lattices. And they provide us also at the same time with excellent detection capabilities, because we can use all the tools that atomic physics provides us with to detect single atoms, to detect a very, very small amount of energies, to do high precision spectroscopy, and so on and so forth. The challenge that we face, and this will be basically is a continuous topic through my talk and through the whole research field, is that the major challenge is that we have to reach low enough entropy states to become competitive with the research in the condensed matter systems. To give you a sense of the scales here, is we typically work at energies which are maybe a 20th of the Fermi energy, whereas in condensed matter samples, it's relatively standard to cool down to 10⁻⁴ of the Fermi energy. However, we can overcome some of these effects by the tunability and by even stronger interactions than you can engineer in a solid. But in order to produce this regime, we have to take efforts to reach low enough entropy states. if we can achieve that, then fermionic atoms in optical lattices, they provide a paradigmatic pathway to do quantum simulation of a solid. And what I mean by this is shown on this transparency. And the goal of the quantum simulation is to understand a system, say a high temperature superconductor or some quantum magnet or a topological state of matter or something where the theoretical understanding is very difficult, by doing an analog version of this or replicating an analog version of this in an experiment with ultracold gases. And then our theory friends, they basically tell us that we can simplify such a complicated lattice structure, this perovskite lattice structure that I show here, to a model system of a simple square lattice, or maybe which only contains a few parameters, and that is in this case the Hubbard model. And then our experiments try to model this Hubbard model, try to find what are the ground states, what are the excitation spectra, what are the different phases that we can observe. This, of course, goes back to the original idea of Richard Feynman from 1980, where he basically suggests this approach to simulating quantum systems. And now with ultracold gases, we really have come a good way in order to make this happening and really gain conceptual understanding of the physics. So for the specific case that I will talk about, namely the spin-1/2 Fermi gas on a lattice, we know already quite a bit. So we know basically the phase diagram exactly if we are at half filling. Half filling means that we have equally many spin-ups and spin-down particles on the lattice, and we have just as many particles as we have in total lattice sites. So on average, 1 particle per site and 50% probability of being spin up or 50% of being spin down. And for this case, we know that there are basically 3 different phases which are depicted on this graph. So if we stick with the repulsive interactions. So if I start on the very left, and that is the conventional phase of a metal that we find usually at high temperatures and at weak interactions. What then happens is basically we have statistical distributions of the spin over the lattice. So we have a large number of fluctuations. Some lattice sites are empty, some lattice sites are singly occupied, some lattice sites are doubly occupied. And these large amount of density fluctuations makes the system compressible. Or if you want to phrase it in the condensed matter analogy, it is conducting. So we can transport the particles through the lattice. If we now start from this point conceptually and increase the repulsive interaction strength, what happens is that these doubly occupied sites, they become disfavored energetically because it costs too much interaction energy to put 2 particles on a side. And what then happens is we cross over from this side to over here, and we occupy the lattice with precisely 1 particle per site. This is a Mott insulator, and that is the state which minimizes the interaction energy. And in this case, the particles, they become pinned to the lattice sites simply by the repulsive interaction. And this is an incompressible state, and hence the name insulator, and we have strongly suppressed density fluctuations. However, there is more that can happen in such a lattice configuration. And this more is where it becomes really interesting, because if we now start from this Mott insulator and lower the temperature, then quantum mechanics dictates that we actually go to a phase transition where this Mott insulator acquires spin order. And the spin order is very peculiar, namely it is antiferromagnetic. So the spins are alternatingly spin up and spin down on adjacent lattice sites. The reason for this fundamentally is the super exchange interaction, which favors that we have singlet bonds across neighboring lattice sites. So this is something that is well understood, and it has also been observed. The question now from the physical point of view, and what motivates our work, is how does this phase diagram look in the more complicated situations? Namely, for example, if we add doping. So if we take out a few particles from the system, or if we add a few particles to the system. Or we can also talk about spin doping, that we imbalance the numbers of spin ups and spin down. And as soon as we go from this idealized case of half filling with equal spin populations, the phase diagram is not yet precisely known. But people have the idea or have the anticipation that there could be further superconducting phases at specific doping levels, for example, which could be related to high temperature superconductivity. And we would like to find out where these phases exist and what the microscopic origin for the superconducting pairing is. So the experiment that we conduct is a relatively standard called ATAMP experiment. So we work with the isotope of potassium-40. We take the two lowest hyperfine states of the potassium-40, and we call these the spin up and the spin down states. So this is our two-level system of fermions that we place into the lattice. We cool the gas down by standard methods, and then we arrange it in an optical lattice, which is constructed out of these 6 laser beams. The 2 green beams that you see here, they form a stack of 2-dimensional layers, as you can see here, where we confine the atoms to a very thin sheet where they move precisely 2-dimensionally. And then we superimpose these 2 pairs of red beams in order to form then lattices in these planes. The detection is done by absorption imaging. So the sample is then illuminated with a laser beam from the bottom, and through a high numerical aperture microscope, we look at the density distribution of the atoms in the lattice. So in this experiment, we do not have single site resolution. It's a very good microscope, but not enough to really observe the single lattice sites. But I will show you later in this talk that we actually don't need single site resolution in order to see the antiferromagnetic correlations. Here's a sample of pictures from this experiment. And what we can do in our setup is, for each and every realization of our quantum gas, we can take 2 observations. So we can either measure the singles occupation and the doubles occupation in the lattice, and that is shown in this example. Or we can measure the spin down density and the spin up density. And that's very important that we do this for 2 measurements for 1 realization of the experiment, because then we can really take correlations measurements between the 2 different pictures. And here is sort of the toy model example of the metal to Mott insulator crossover in the singles and doubles. So this is all done in the harmonic trap, these experiments. So we expect to have a higher density of the particles at the center of the trap, a lower density at the edge. And here are the 2 pictures that we take. That's the singles picture. You see that the singly occupied sites, they're at the edge of the trap cloud, and the doubly occupied sites, they're at the center. So in reality, these 2 pictures are of course superimposed. So these doubles fill precisely the hole that the singles have, and we displace them here for clarity. And then we can take density profiles through these clouds, and then you see here in red is the doubles density, in blue is the singles density. We can just add them, and this then accounts for the total density distribution. And you see directly here the density reflects the shape of the harmonic trap, which immediately signals that we have a compressible metallic state. Now, if we increase the repulsive interactions, so this was a ratio of repulsive energy to kinetic energy of 1.6. If we now go to 8, then you see that we get many, many more singly occupied lattice sites, and the doubles slowly fade away. And at U over T equals 12, we only have singly occupied lattice sites, and the doubles have all gone. And you see also that the density is now flat in the center of the trap, which signals that we have an incompressible phase, and that is the Mott insulator. So we can, from our density pictures, we can directly see this crossover very, very clearly. Okay, so this was about the introduction and the techniques that we use. So in this talk, I would like to discuss 2 experiments that we've conducted last year. One is about the interplay between attractive interactions and repulsive interactions in the lattice. And the second one is the bilayer Hubbard model, where we actually couple 2 of these planes and see what happens to the antiferromagnetic state in these planes when we introduce this interlayer coupling. So let's start with the interplay or between the symmetry between attractive and repulsive interactions in a normal two-dimensional Hubbard model. So here is the textbook picture of a band structure of particles in a lattice. So here on the horizontal axis, there is quasi-momentum ranging from one edge of the Brion zone to the other edge. D is the lattice spacing, so minus pi over d to pi over d is just the first Brion zone of the lattice. And we have a certain dispersion for the lowest Bloch band in the lattice. So now what happens when we start to fill this lattice? So if you have 0 particles, you just have the vacuum state. And now you start to fill in particles into your band structure. You start to occupy the particles near the bottom of the band and start to fill up these states. And at some point, when you've filled in all the particles that you have, you've reached the Fermi energy. So we basically started from the vacuum state, added particles, and ended up here in a certain state. Now, what happens if we do conceptually, at least, just the opposite? So let's suppose we start with a completely filled band, so band insulator, and start to remove particles from this. And in the theoretical language, this would mean we add holes to the system. So we start from the very top now and start to add holes and holes and holes to the system. We also reach a certain Fermi energy then. And the fantastic thing is that this situation of adding particles or adding holes to the system is completely symmetric. So we can express all the physics that we can express in particles starting from the bottom of the band equally well through having holes starting from the top of the band. So this is the particle hole symmetry of the ideal Fermi gas in the lattice. Now, we don't work with ideal Fermi gases, but we work with spinful gases and interactions. So the question is, what happens to this elementary particle hole symmetry for a spinful Fermi gas? Well, there we have to be a little bit more careful because we have to properly account for the spin of the particles. But we can still define a particle hole symmetry operation on this, and that is shown here at the very top. So this particle hole symmetry operation there would be a spin up remains unchanged and a spin down becomes a spin down, but with a certain prefactor of the phase, which depends on the lattice index. And what this transformation does, it converts or it maps spin up particles onto doublons and spin down particles onto holes. So that is it's a spin particle hole symmetry transformation. It is slightly different from the ideal Fermi gas, but in essence, it does the same thing. So here's the pictorial visualization. So we say blue is spin up and red is spin down. Then this transformation converts spin up into doubles and spin down into holes. So if we say we accept that, what happens then to our phases if we do this particle hole transformation? So let's say we start out here from this Mott insulator, which has on average 1 particle per side, and there can be the occasional fluctuation like here or like here, but it has pretty uniform occupation. And wherever we have now a spin up particle, we get a doublon after the transformation, and wherever we have a spin down particle, we get a hole. So that would be basically a transformation of a Mott insulator into a gas of local pairs. We can take this even further if we ask what happens to our antiferromagnet, where the spins are really alternatingly ordered across the lattice. Then we actually end up with an arrangement of pairs on every second lattice side. And this is a charge density wave state of the pairs. So we get here a mapping between the different, very different phases. So for example, the charge density wave phase would be a compressible phase in the charge domain, but the antiferromagnet, of course, is an incompressible phase in the charge domain. But we will see that we can actually map these properties onto each other very well. So how this works is if we write down the Hubbard Hamiltonian and work in this particle hole transformation, then we see that leads to a remarkable symmetry. Namely, if we change from attractive to repulsive interactions, the roles of the chemical potential and the Zeeman fields, they just flip. The Zeeman field measures basically the spin imbalance between the systems. So it's called the Zeeman field because in solids, in order to have different chemical potentials for spin up and spin down, you would have to introduce a large magnetic field. In our case, with the ultracold atoms, we just throw in a few more spin up particles as compared to spin down particles. That's different, but it's still called a Zeeman field for historical reasons. Yeah, so that's what we want to observe is so that actually when we change the interactions from attractive to repulsive, that all these phases map onto one another, but the chemical potential becomes now the spin imbalance and vice versa. And Thierry Jamaki and co-workers, they have worked this out very carefully in already 10 years ago. And they actually show that every phase on the repulsive side, say for spin balance, but as a function of doping, has its matching correspondence for attractive interactions and magnetization now as the doping parameter, but for zero doping. And so, for example, the Mott insulator, as I showed you, maps to the local pairs. The antiferromagnet maps to the charge density wave of the doublons. The D-wave superconductor that is somewhere expected to be down here maps onto a D-wave antiferromagnetic phase and so on. So, and this mapping that is exact under this particle Hole transformation, that of course provides you with a fantastic opportunity that you can possibly identify certain phases better in momentum space or in real space, and this mapping gives you the opportunity to choose whatever detection method you have available to detect this or that phase. And so far this was only a theoretical concept, and we would like to see how well this is actually realized in the experiments. Okay, so the first thing that we did is we went to half filling. So the situation that I described initially, we have equal number of particles in spin up and spin down, and total number of particles is equal to the total number of lattice sites. On average, 1 particle per site. And now we change the interaction and look at the single occupation and the double occupation. And what you then see is that if we go to repulsive interactions, which is the right-hand side of this graph, of course, the amount of single occupied sites goes up because it costs interaction energy to have doubles, and the amount of double occupied sites goes down accordingly. If we're at 0, we have 25%, that's just statistical. And if we go to the attractive side, of course, we get more doubles because the particles are now attracted towards one another, and we reduce the amount of singles. And this is perfectly mirror symmetric about this U equals 0 point. And that is the first indication that this particle Hole symmetry actually works. However, this is at half filling, so that's chemical potential of mu equals 0. So this means also the Zeeman field is set to be 0. So we don't see yet this transformation of chemical potential into Zeeman energies. So for this, we have to go away from half filling. And what we do in the experiment, as I showed you in the very first, or one of the very first slides, is we measure the density as a function of position in the harmonic trap. And if we assume that our sample is well thermalized, we can assume that we have a constant chemical potential throughout the trap. But this means locally the chemical potential changes if we believe in a local density approximation. So this means by extracting the densities from certain points of the picture, we can extract densities corresponding to different values of the chemical potential. And that is shown in this left graph here. So you see in gray the density of the doubly occupied sites for different values of the local chemical potential. And in green, you see the density of the singly occupied sites, so spin up minus doubles. And you see here at mu equals 0, the singles, they peak. That is a consequence of the particle Hole symmetry. And we see that for attractive interactions where we are at, we have way more doubles than we have singles, of course. So this would be the case where we have a spin imbalance and attractive interaction. So the Zeeman field is 0, and the interaction constant U is smaller than 0. Now let's reverse this. Now let's go to the repulsive side and find out about the spin imbalance. So this measurement is slightly more complicated. So we have to create spin imbalances by hand and then measure the same property again. So here is the Zeeman field. So that's the amount of spin imbalance that we have. Here is the balance case 0. And at 2 we have already a significant spin imbalance. And you see the spin imbalance, so the spins are shown as the spin up and the spin down densities in red and blue here. Now, what we're interested in is finding out what is the chemical potential. And what we basically do is we measure for the 2 different spin densities the corresponding chemical potentials here and here, here and here. And now we want to map that information to the spin balanced case. So now we take all of this data and plot this onto one graph. And on the one hand, so for attractive interactions, we plot the doubles density as a function of the chemical potential. And for the repulsive interactions, for the exact opposite value, we plot now the density at chemical potential equals 0 as a function of the chemical potential. And you see that these two curves collapse directly onto one another. There's no free parameters in there. Everything is just scaled in units of the tunneling matrix element, and we have a perfect collapse of the data. And this shows that for our realization of the Hubbard model, we really have a very good realization of this particle-Hole symmetry. Sorry, that was my mistake. Okay, sorry. And now we can take this one step further and ask, so we see that the density is precisely mapped between repulsive and attractive interactions if we swap chemical potential and Zeeman fields. But does this also apply to other thermodynamic variables? And here we show this now for the compressibility. So for the repulsively interacting gas, we know that we have a minimum of compressibility when we enter the Mott insulator phase. And we measure the compressibility simply by taking the derivative of the density with respect to the chemical potential. So it's basically the slope of this line provides us with the compressibility. And that is shown as the red data points here. Again, everything is just scaled in the tunneling matrix elements. There are no free parameters in this. Now, for the other case, for attractive interactions where we have these local pairs, we have to ask the question, what is the equivalent of the compressibility in the density sector, but now in the spin sector? And that is, of course, the spin susceptibility. So it's the question of whether we can actually disintegrate these local pairs into 2 free spins. And we measure the spin susceptibility spectroscopically, and then we observe directly how the spin susceptibility precisely maps the behavior of the compressibility for the density sector. So this shows that we really have a mapping between the thermodynamic properties, thermodynamic quantities, between the density domain for repulsive interactions and the spin domain here for the attractive interactions, just by exchanging the roles of the chemical potential and the Zeeman field. And this, of course, is very encouraging if you now would like to go on and explore the mapping between the other phases that I mentioned. So the antiferromagnet with a charge density wave of the pairs, for example. You can basically choose whatever detection technology you have available, either local measurements or momentum measurements, to detect one of the phases, and then you know that the other phase exists also for the opposite configuration. Okay, so this brings me now to the second part of the talk that I would like to discuss with you, and that is about the bilayer Hubbard models. So far I've been talking about a single two-dimensional layer with spin 1/2 particles on the lattice in there. So this standard two-dimensional Hubbard model. And we are now interested to see what happens when we actually allow coupling between adjacent planes. So to this end, we implemented an additional superlattice in the vertical direction, which allows us to couple always pairs of these layers to one another with an adjustable coupling strength. And one can qualitatively understand relatively well what we can expect to observe there. And if we start from the weak coupling limit, so that the tunnel coupling between the layers is very much smaller than the coupling within the layers, then we can expect that the physics in each layer is only very weakly perturbed. So we will get antiferromagnetic ordering in these individual two-dimensional layers. Now, if we go to the opposite situation, that we have a very strong tunnel coupling between the layers, then it will be advantages for the system to form strong bonds between the planes, so as depicted here by these green shades. And for low enough temperature, these bonds will become singlets along these bonds. So we would have an array of singlets along the bonds, but these singlets between the bonds, they may not be correlated with one another in the plane, because the tunnel coupling within this plane can be very small. So what we would expect to see in this bilayer Hubbard model basically is a crossover of magnetic ordering from in-plane for weak coupling to intra-plane for strong coupling. There has been a lot of theory on this, of course, because the bilayer Hubbard model has been studied extensively in the literature, because it's sort of the intermediate step between a three-dimensional Hubbard model and a two-dimensional Hubbard model. And people have actually investigated that there is actually at zero temperature a quantum phase transition between these two ordered states. Of course, here we at finite temperature, we will not see quantum critical behavior here with the temperatures that we currently have. But still, even above the quantum critical point, we will see the crossover between these magnetic orderings. So the experiment roughly looks the following. We now have these coupled planes, this one, this one, this one, this one. And in order to increase our chances of observing this, we've additionally made flat potentials in these layers. So we use a DMD to compensate the harmonic trapping potential. We use then some boundaries here where we cut off the density. So we basically create a flat bottom bucket where we collect the atoms, and then some atoms spill over in these entropy reservoirs here. And then we get a very cold and dense sample at the center, which spans around 80 lattice sites approximately. And here you see an in situ image of this. So you see the dense core, and then some atoms scattered around here in very low density regions. And we hope that they also contribute to reaching low temperatures, because they can take up some of the entropy that is squeezed out from the core system. Okay, so now the question is, how can we detect the antiferromagnetic order within the plane without actually having single site resolution or having a quantum gas microscope? And the experimental protocol that we use for this is shown here. So conceptually, it's very simple. The implementation took us quite a bit of time. So suppose you start from this antiferromagnetically ordered state. So I've just deliberately chosen here the z axis as our basis, but this works actually in any basis, which is good. So we have on alternating, or on neighboring lattice sites, we have the alternating spins, spin up, spin down, spin up, spin down, and we want to measure basically the staggered correlation function. So we want to measure how the staggered correlation function, so including the sign of the spin, decays with distance. So what we do in the first step is we implement a pi/2 rotation of the spin. So the first spin is flipped then into the equatorial plane in this direction. The second spin is flipped into the equatorial plane in this direction, and so on and so forth. So this does nothing. It's a global operation on the antiferromagnet. We just rotate the whole thing into the plane. And now we apply a magnetic field gradient, which leads to a precession of the spins. And the precession rate will depend on the location of the atoms. Actually, we can direct this magnetic field gradient into any direction along the lattice, so we can conduct this measurement into any k vector in the Fermionic zone. And if we have done the time evolution for just the correct time, then the spins which have been precessing, they have essentially all lined up into one direction. We apply another pi/2 pulse, which flips the spins back into the same direction. And now we have converted this initially antiferromagnetic state into something which looks like a ferromagnet. And the ferromagnet is much easier to detect because with our imaging, we can just measure the sizes of the domains. And basically, we convert the measurement of the staggered spin correlation function into a measurement of a homogeneous spin correlation function. And by choosing the direction of the gradient and the strength of the gradient, we can measure this for any k vector in the lattice. For this experiment, we're particularly interested in the pi direction because this is where the antiferromagnetic correlations are. But we have also done this for other values within the Fermionic zone. Okay, so if we conduct this measurement as a function of the coupling strength, then we see the following. So the red data points, this is the measurement of the staggered magnetic structure factor at wave vector pi. So these are the antiferromagnetic correlations. And you see they have some dependence on the interaction parameter. And we compare this to some DQMC calculations, which we have done with some available code. And we see very good agreement. But the question is, where is actually our baseline for this experiment? So what do we compare to when we say we have antiferromagnetic correlations? And we have basically two ways that we can compare with. One is the uniform structure factor. So that is basically measuring without the spin rotation the same thing. And this gives us the baseline. That is, these are the green data points down here. And the other thing is the local magnetic moment. So that is just the distribution of the on-site spins without taking into account nearest neighbor correlations. And these are the blue data points. And the uniform structure factor and the staggered structure factor, they should be symmetrically around this local moment, and as you see here. And we basically see that for low coupling between the bilayer structure, we have a large excess at the staggered structure factor as compared to the local moment. And as we go to increased coupling between the planes, this goes away, and essentially all the magnetic information goes away. Everything collapses onto the local magnetic moment. And this is basically the case, the situation where we lose the magnetic correlations in the system completely. So by tuning this interlayer coupling from 0 to 5 in units of the intraplane coupling, we can tune from nicely antiferromagnetically correlated states to non-magnetically ordered states in each of the planes. The question now is, what happens in the opposite direction? So how can we now compare this to the intralayer correlations? And here we use a technique that was developed a few years ago in the groups of Tilman Essling and Emmanuel Bloch. And that is basically that a technique how you find out whether in this double well you actually have a spin singlet or a spin triplet state. And you do this by ramping the barrier in the double well appropriately. And then the singlet state will map into two spins in different vibrational layers of the lattice. And the triplet will map onto two spins in the same vibrational layer. And this is then offset, of course, by the interaction energy. So this is a technique that we apply to the two layers of our bilayer model. and then we detect basically how many atoms do we have either in the separate bands of the Z lattice, or how many are in the same band but shifted by the interaction energy. And so after appropriate normalization, we can now then state what are the interplane magnetic correlations, and you basically see the exact opposite behavior. You see that for low tunnel coupling, there are no interlayer magnetic correlations. So it's just uncorrelated mixture between singlet and triplet states. And as we increase the intralayer coupling, these magnetic correlations between the layers, they start to build up. And if you remember the previous picture, it's exactly the opposite behavior. So that really shows you that there is this crossover between the two magnetic orderings. So we can try to quantify that and find out what is about the range of the interaction of the tunnel coupling where this happens. So we basically then can plot here on a scale that 0 means all correlations are between the planes, and 1 or all correlations are in the planes. And we now investigate this for several interaction strengths. And if we take the 50% point, then we see that this is around between 2 and 3 in units of the interplane tunneling matrix element. This number, surprisingly, is not that far away from the prediction of the quantum critical point, which is at 1.6 for the large U limit. And it's comparable also to other numerical simulations, which mention it in the range of about 2. We can say that we see the expected behavior here for this crossover between these two magnetic phases. And now we come to the question: what is actually the state of these singlets? So if you're talking about the quantum critical point, then it was shown that the singlets would actually form a band insulator. So it's not just a singlet pairs, but it's really an incompressible phase in the plane that is composed of these singlets, which are between the planes. And the question is, can we actually see that there is a band insulator of these singlets? And the answer, unfortunately, is no. Firstly, we're not precisely enough at half filling. So we're at a filling of 0.45 or something like this. And we're not precisely at 0 temperature. But however, what we have done is we have measured for this, we have measured the compressibility in the plane by applying magnetic field gradient, trying to make the atoms move and see how they react to this perturbation. And there we see the behavior that the interplane compressibility actually goes down as we increase the coupling between the layers. So that is shown here. So that's the compressibility. It has a certain value. So the antiferromagnetic state is not precisely incompressible, firstly because we're not precisely at half filling, and also because the antiferromagnetic still has some density fluctuations in order to form the super exchange interaction. But so it has some residual compressibility. But if we go on and increase the coupling between the planes, we actually see that the compressibility goes down. And we believe that this is a first hint at that this singlet state, or this area of the singlets, indeed is more insulating than the standard two-dimensional Hubbard plane is. Okay, so with this, I come to the end of the presentation. So basically, I've showed you two experiments. One is what was discussing the mapping between the attractive and the repulsive Hubbard model and the particle-hole symmetry in this spin-full system. And the other one was the bilayer system with the controlled coupling between the planes and the crossover between the two different magnetic regimes. In the future, we would, of course, like to see if we can reach lower temperatures and lower entropy states in the lattice. And there, the bilayer system could actually help us. And the bilayer system also could allow for a novel base of reaching superfluid phases in the lattice in a slightly different way from the standard two-dimensional Hubbard approach. because the coupling between the layers gives you additional degrees of freedom that can actually enhance superconducting pairing under certain circumstances. So this is where we would like to head to in the future. And with this, I finally would like to thank the people who did all the work. Particular, that was the PhD thesis of Marcel Gall, Jeffrey Chan, and Nicolas Wurz, who have all graduated or are now in the process of graduating. And now we have a new team on this experiment. And I hope we will see some exciting results from them in the future. Thank you very much for your attention.
Yeah, thanks a lot for this very nice and clear talk. Are there any questions? If yes, just unmute yourself and start talking.
Hi, I had a question about the imaging of the bilayers. So the correlations that you measured, after the spin flip, the ferromagnetic or the antiferromagnetic correlations, were those measured for each layer, or are they sort of the sum of the two layers?
No, we measure this for each layer.
I see. And
they're the same for 2 layers. Yeah.
I see. And I was just curious how you measure them for the 2 different layers.
And we apply a magnetic field gradient in the Z direction in order to slice out the individual layers for detection. So if we, let me just go back maybe to my intro or this transparency. So what we do is we create a 3-dimensional cloud of atoms. We load this into this stack of planes. And the physics is happening in all planes simultaneously. But for detection, we select one of these planes by magnetic resonance. So we apply a vertical gradient, slice out one plane, and then do the detection only on this plane.
I have a quick question for the correlation in the transverse plane, like in the bilayer thing, because it seemed to saturate on the plot that when you had like correlation as a function of t, so it starts up and then it saturates to something that looked like a lower value than what you had for the antiferromagnetic ordering or whatever. So I just wanted, so I understand the rising up of the correlation, but why does it flatten out, and should it flatten out to some higher value, or what should we expect here?
So the question is, how do you compare these numbers that we assign to these vertical axes?
No, it's like, how does the correlation compare in the bilayer system compared to in just one layer system, the correlation between different sides?
Okay, that is basically shown on this graph, right? Sort of here we've normalized this appropriately, and now if the data point is 1, then we have 0 correlations between the planes, and down here is the opposite.
Yeah,
and
so exactly.
You can see how this behaves as a function of the interaction.
But so here, if we take the same normalization, it seems that intraplane you reach a correlation that you label as 1, but in between the different planes you saturate to a lower value. I think 0.1, if
yes.
I correctly.
Yes. Yes, sort of. You have to be a little bit careful with these numbers, because, for example, here in this case, we would say there are no magnetic correlations anymore, but we have because the staggered structure factor coincides with the local moment. Yes.
Okay, so you say it's more measurement thing than actually the correlation flattens out?
No, I think this correlation that flattens out. I mean, I think in this case, essentially we'll be limited by temperature, right? Sort of once you increase the coupling between the layers more and more, you will not get more singlet, except for your impurity, which contribution of the triplet state, which comes in through temperature, finite temperature.
Okay, but at a lower temperature, you would expect this interlayer correlation to go higher, right?
Yes, I think that's a function of temperature, yes.
Okay.
More questions?
Yeah, maybe I can ask about, Wolfgang Kederle. Hi, Michael, nice to see you.
Hey.
I want to ask about the selection of the bilayer system. So my understanding is you have a 3-dimensional, so you have a stack of pancakes. And now you want to single out a bilayer system, and this must be done with magnetic gradients and such.
Yeah.
So you explained before, if you have a stack of pancakes with magnetic gradient, you can just selectively image one of them.
Yes.
But how do you create your system of two layers which are coupled, embedded in all the other layers on top and the bottom?
Okay. So we basically start out from this configuration, which is the standard array of two-dimensional Hubbard models. Then we superimpose a super lattice in the vertical direction, which is precisely phase matched with this lattice, and we split every of these layers.
I missed the super lattice. Okay, the super lattice is creating pairs of pancakes, and
yes.
then you have dedicated pairs, and it's clear that only one pancake is talking to the other one. Okay,
yes.
Okay.
Mm-hmm.
Actually, regarding this, somewhat hypothetical, but could you also then weakly couple one bilayer system to another bilayer system and so on? Because I think that's what like some of these cuprates are actually, right?
That would require yet another lattice. If you want to do it pairwise, bilayer pair with bilayer, that would require another optical lattice. We could, of course, globally increase the coupling between all bilayers, but so this is something we would not be so inclined to do, because as you see in the sketch here, we have different densities in the different planes. So at some point it becomes difficult to compare this. And that's why we conduct all these measurements only in one layer of this whole thing, namely the one at the center. But in principle, that's possible if one takes this extra effort. Yes.
But you couldn't use the one super lattice that you have and basically increase the tunneling between two bilayers by reducing the strength of the super lattice that you already have. Wouldn't that also work?
No, I think the super lattice always controls pairs, right? And now you can now swap. You can now make the super lattice stronger or weaker, or you can change the phase, and then you can select which pair of layers you're connecting. But if you want to connect pairs with one another, you can ramp down or up the main lattice. But this would couple all at the same time. This would not couple one pair of bilayers.
Oh yeah, okay. But that was what I was thinking about. Yeah, okay. Like have like a whole stack of bilayers, basically.
Oh, this can be done. Yes.
Okay, cool. More questions. I actually have one more question. You mentioned that you are not really at half filling. So was this on purpose, or is there a technical reason that you were not at half filling?
Well, the reason is more technical, right? Sort of the question is, how can we end up with a nice bilayer system? So what we decided to go for is to start with a band insulator and split it into layers. And if you don't have a zero temperature state, you cannot make a perfect band insulator. So our band insulator inevitably has some holes in it, which reflects the temperature. And this amount of doping is then translated into the bilayers. So we've decided to make the split equal, so that we have the equal doping in both of these bilayers. But with this preparation technique, we can never reach full half filling in both bilayers unless we're at zero temperature. So yeah, it's a technical thing.
Maybe a naive question on your mapping from the antiferromagnetic phase to like the ferromagnetic phase. Does that require any pre-knowledge of like the phase boundaries, or what would happen if you had like some patches evolving in the system? How would they map to ferromagnetic patches?
No, it doesn't. It doesn't require any knowledge. It's what we like about the system is sort of normally when you create these antiferromagnets, you only know that the antiferromagnetic order is sort of in one direction, and there's the SU2 symmetry, which can rotate this direction into any direction in space, if you will. And there is some ambiguity about detecting these antiferromagnetics. The nice thing about this method is that it works for every realization, because the process just rotates the spins from wherever they start and measures after the second spin flip, where they are now pointing into the same direction or not, irrespective from where they started from. And so we don't have to put any information into this except for the duration and the time of the gradient, which determines the k vector at which we're measuring.
Okay. Thanks.
Any more questions? Okay, let me ask one final question. You mentioned in the end that you might get superfluidity in the system. So how would you go about probing that with your system?
We don't know. Sort of, we have been sort of the first one. The first signatures would be try to measure correlations, but if you want to measure superfluidity, you probably have to measure something movable, or measure with something movable in the system. So either move the lattice, accelerate the lattice and see the response to that, or move an object through this. Otherwise, I think really proving that you have superfluidity in such a system with repulsive interactions is difficult to convince other people if you cannot really see that.
Okay, cool. Yeah, thanks a lot. I think we have had plenty of questions, so if there is nothing else urgent, then let's thank Michael again for this very nice talk.
Well, thank you for your attention.
Thanks.